Good afternoon, everyone. I am Robert Free from the Department of Water and Sanitation, and today I'm going to be talking about the groundwater level trend analysis within the Highveld-Vegter region. So, presentation layout, let's have a quick look here. So I'm going to take you through the aim of this project, as well as the background information being the locality, climate, geology, as well as hydrogeology. Then I'll be taking you through the methodologies, the results and discussions, and then finally the conclusion and recommendations. So the aim of this project was to determine the groundwater level trends within the central Highveld-Vegter region over 2 consecutive hydrological years. Now these hydrological years are the 2022-23 hydrological year up until the 2023-24 hydrological year. Now just note that the hydrological years stretch from October to the following September. Then from these trends that we determined, we were able to identify problematic areas within the study area. And then from there, we were able to identify if these fluctuations were caused by anthropogenic or natural processes, and then finally provide recommendations to improve on these problematic areas. So the locality of the study area, the central Highveld-Vegter region is one of many Vegter regions in the country. It stretches over the Gauteng province, the Free State province, the Mpumalanga province, as well as the Northwest province. But the majority of the study area is located within Gauteng. So therefore, when looking at the climate for the study area, we were analyzing the rainfall data for Gauteng. And then as you can see, for the first hydrological year, there was above normal rainfall for the 2022-23 hydrological year. Comparing that to the following hydrological year, we see that there is much less rain during that year with below normal rainfall. Now moving on to the geology for the study area. The geology is very vast here, but there's emphasis on the dolomitic formations within the Transvaal supergroup under the Chinispoort group. These dolomitic formations played a crucial role in this project. Now the hydrogeological background for this study, we see that there were 3 different aquifer types: the fractured aquifers, intergranular and fractured aquifers, and then also the karst aquifers, following those boundaries of those dolomitic formations that I mentioned. And then these aquifers we then classified into your major and minor aquifers. Your karst aquifers were classified as your major aquifer, and then your other groundwater systems classified as your minor aquifer systems. No poor aquifer systems were identified in this study area. Then looking at the groundwater use data, we saw that 58% of the groundwater is allocated to the urban industry. And now moving on to the aquifer vulnerability map, we can see that the major karst aquifer had a very high vulnerability towards surface contaminants, whereas the surrounding groundwater systems only had medium to low vulnerabilities. And then looking at the aquifer quality, the dominant water type here is the calcium magnesium bicarbonate type, which is a characteristic of a shallow fresh recharge and also is a characteristic of a dolomitic environment. Now, the methodologies that we used to determine the fluctuations, firstly for a short-term analysis, we used a very simple formula here. We took the average groundwater level of the 2023-24 hydrological year and subtracted the average groundwater level of the 2022-23 hydrological year, and then categorize the fluctuations into 5 different classes, being your major decline class, where you have your groundwater level decline with more than 5 meters, your moderate decline class with the groundwater level decline between 5 and 0.2 meters, your stable water level, obviously with no major fluctuations between the 2 years. Then the moderate increase is where your groundwater level increases between 5 and 0.2 meters, and then your major increase, your groundwater level increasing with more than 5 meters. Now regarding our long-term analysis, we use time series plots in the form of hydrographs. Now this uses a Python code to determine an average normalized groundwater level per borehole, and from these normalized groundwater levels, we were able to determine 20-year trends, 10-year trends, and 5-year trends. Now for the results and discussions, those yellow plots are the boreholes that we used for this project. As you can see, majority of the boreholes plot within the major karst aquifer. Therefore, the discussions to follow will only be based on that of the major karst aquifer and not the entire central Highveld-Vegter region. So the groundwater levels for the 2 hydrological years, we can see that almost 50% of the boreholes had groundwater levels between 10 and 30 meters below ground. We can also see that the deeper groundwater systems showed no changes between the 2 years, whereas your shallower groundwater levels did show minor changes between the 2 hydrological years. And then finally, moving on to the fluctuation results, we saw that 80% of the 95 boreholes that we analyzed had moderate declining groundwater levels of between 5 and 0.2 meters. The figure at the top there also shows you that, for instance, we were able to identify these problematic areas where those boreholes plotting within that circle were located close to a mine. Therefore, it could be a possibility of over-abstraction. Yes, okay, moving on. So now what we try to do here is we try to determine the cause of these fluctuations, whether it being natural or anthropogenic. The figure on the left, we can see the groundwater level fluctuations, where you have your darker areas showing your decreasing groundwater levels, and then the figure on the right showing your abstraction volumes. Now we can see there's a clear correlation between the two, where your groundwater level decreasing areas correlate well with your areas having high abstraction volumes. Now this figure is just the entire Central Highveld-Vechter area with its abstraction volumes, showing that majority of the water is being abstracted within that karst aquifer, but we also have high abstractions outside this aquifer, emphasizing the importance of also obtaining data from outside, representing the entire Vechter region. Now this is a hydrograph for a single borehole. It's just for me to show you the importance of having both long-term and short-term analysis. So if you look at this in a 5-year term, you can see there is no real concern for this borehole. The borehole is predominantly stable, but when zooming in between those two black lines, you can see that there was a period of time where we had very decreasing groundwater levels. Therefore, you can determine a period where the aquifer experienced stress. So therefore, it is also important to look at it in both long-term and short-term. And then finally, moving on to the hydrograph analysis, which is long-term, we can see that the 20-year trend, the 10-year trend, and the 5-year trend all had positive slopes, which shows you that the groundwater levels were increasing in the study area, especially the 5-year trend having the steepest positive slope. This is also just to emphasize that almost 50% of the slopes were positive, indicating increasing groundwater levels, but where only 6% of the slopes were strong negative, indicating decreasing groundwater levels in this study area. Now, in conclusion, from analyzing the major karst aquifer within the Central Highveld-Vechter region, we saw that the deeper water levels showed little to no changes compared to that of the shallow water levels. 80% of the boreholes showed a moderate decline in the groundwater levels, which we determined that the cause of this was anthropogenic of nature due to the high abstraction volumes. The groundwater level fluctuation could also be affected by the changes in rainfall patterns, where we saw that the first hydrological year had much more rain than the second hydrological year. And then also the long-term hydrograph analysis showed trends of increasing groundwater levels, which is opposite to that of the short-term 2-year analysis. This is also just to emphasize the importance of looking at this problem in a long-term and short-term. Now, for the recommendations, it was recommended to expand the monitoring network in order to obtain more data outside of this karst aquifer to get a representative view of the entire Vechter region. Now, those plots in red are boreholes with licenses. Therefore, we can obtain monitoring data from those boreholes to help us expand this monitoring network. And then also further investigations is needed for these problematic areas to determine if we actually need to modify the allowed abstraction volumes for these licenses. And then also further studies needed to compare the climatic impact versus abstraction rates for the groundwater levels to see if climate or if natural processes or anthropogenic processes in the future have a larger impact on this study area. Thank you.
Okay, thank you very much. I think it was exactly 10 minutes. We really appreciate that. Okay, so now we're going to move to the point of questions. If there are questions or comments, guidance, inputs. I see there are 2 hands. This side, I don't know, this side is quiet. And now I'm going to start pointing to people this side without even raising the hands. Okay, 1, 2, 3, 4. So we're going to start with Kevin and then the other hand that side. So let's start with Kevin. Yeah.
So my question just relates to whether you've correlated to the water level fluctuations to rainfall, and is there any relation to rainfall intensity or rainfall amounts? Thank you.
Maybe let's get 2 questions so that you can answer. Yes.
Okay, thank you. My question is that in your presentation you've seen rainfall data of 2 years. My concern was that 2 years is quite a short period. Maybe if you'd have given us a way forward on maybe a 5-year period of the rainfall to see how that affects the changes. Thank you.
I don't know whether that was a question or it was just a comment to improve, but maybe let's take the third one. Just give him quickly.
Thank you. My question is, the study area, you said that it's mostly dominated by factories. So in your study, did you also get to look at the water quality, considering that it's factories in the study area? Thank you.
Yes, answer this.
Sorry, can you please repeat that? Okay, thank you for those questions. So for the first question, regarding the correlation for the rainfall. So I mentioned in the recommendations that going forward, it would be advisable to also look, that's where the long-term rainfall data also comes in now, to look at the impact of the groundwater levels, looking at climate in a long term as well. Because here we only kind of looked at it as a abstraction volume point of view, because we saw that the rainfall was difficult to correlate with the declining groundwater levels, especially with the data availability that we had during that time. But I can comment that there was another region that we did analyze where we actually saw how rainfall impacted that region. We could see that clear correlation of how the increasing rainfall actually contributed to the boreholes showing increasing groundwater levels. And then also, thank you for that comment. That is, I take that into consideration going forward for increasing my rainfall data over longer periods. And then regarding the factories and water quality, if I understand your question. So we did, in this report, I did have maps for quality, especially focusing on, if I can remember correctly, I think it's fluoride levels. There was a specific area where we had very concerning fluoride concentrations within the groundwater, and that specifically was located close to mines, because this study area is very concentrated with like mining activity. So I did look at it and like quality-wise, but I didn't go deep in the quality because I focused more on the groundwater level fluctuations instead of quality. But I would like to, in the future, because quality can also give you an indication of recharge. So that will tell you how rainfall affected your groundwater levels. So going forward, quality would also be considered for this project. Thank you.
Last hand, I think there was a hand this side. Just be quick. We're running out.
Thank you. Mine is on the sensitivity of one well compared to the other. If speaking of the fluctuation, have you been able to observe, maybe through a sensitivity analysis, how a nearest well influences the drawdown in the other well?
So you're asking like in the two boreholes in proximity to one another, how the one influences the other?
Yes.
No, I have not done that analysis, going deeper into the single boreholes, as this was a total of 95 boreholes, so it would take a longer period of time to do that analysis to see how each borehole can affect one another.